Here we have exhaust from two storage bins at a fiberglass plant that are combined and passed through a cyclone that provides 95% particulate removal by weight. So we have bin A and bin B. Exhaust comes from those two. It's combined together and it goes through a cyclone. A cyclone removes particles larger than a certain size and at 95% efficiency. Measurements from the bins are shown below. Find the rate of solids discharged from the cyclone and the concentration of solids remaining in the air being exhausted from the cyclone. So your dirty gas comes in from the side of the cyclone here, and then it kind of whirls around inside, and the large particles slam against the walls because they can't make that turn, and then it comes out the top, and you have clean gas coming out the top because the particles have collected along the sides of the cyclone, and then they fall down to the bottom, and this is the solids discharge. And then there's some solids remaining in the air coming out, like 5% by weight. Looking at the bins, we are given the flow rate of each in units of actual cubic feet per minute, 3,000 and 2,500. We are giving the loading, or really the concentration of particles in the exhaust of each of those bins. It's in units of grains per standard cubic foot. A grain turns out to be a unit of mass, and I'll show you what the conversion is to grams. In bin A, we have 15 grains per standard cubic foot of silicon dioxide, SiO2, and from bin B, we have 10 grains per standard cubic foot of sodium carbonate, Na2CO3. The exhaust of the bins is at different pressures. Bin A is at 16 pounds per square inch absolute. Bin B is at 17 psia. For comparison, atmospheric pressure is 14.7 psi, so it's slightly above atmospheric pressure. The temperature of the bins is 90 degrees for bin A and 110 degrees for bin B. So the first question here is, what is a grain? It turns out that a grain, abbreviated GR, is equal to 64.80 milligrams. And that comes from, who knows why, but it's 1/7,000th of a pound. We'll use the conversion to milligrams. As always, I like to start these problems by drawing a diagram. Here are our two bins, A and B. They have exhaust coming out of them. Which is combined and then sent to a cyclone, which I'll draw as an upside down cone, which is kind of the shape of it. And then we'll draw our different flows and concentrations. We're going to have a flow rate from A of QA with some concentration in the exhaust of C sub A, and we can combine those to get a mass flow rate coming from bin A. Likewise, we have a flow rate from bin B, a concentration associated with that flow rate, and we can calculate the mass flow rate coming from bin B. We'll combine those and we'll get some total flow rate called Q total. We'll have a total concentration and then a total mass flow rate. With the cyclone, we have a mass flow rate out the bottom, which is the discharge rate, which is 95% of what comes in. So we're told that efficiency. And then we have what comes out the top, which is our m dot in the exhaust, which is going to be 0.05 times m dot total. Next, we're going to combine the flows and find Q total. The flow information we're given, though, is for bin A and B, and it's in different temperatures and pressures for each bin. So what we need to do is to convert from actual conditions to standard conditions. So we can do this directly by starting with QA in actual conditions, which was 3,000 cubic feet per minute. Then we multiply by the actual pressure, which was 16 psi, divided by standard pressure, which is 14.7 psi. And then we multiply by standard temperature. We're given temperature in degrees Fahrenheit. And so just like with Celsius, we go to an absolute scale of Kelvin. With Fahrenheit, we go to an absolute scale of Rankine. And standard temperature in Rankine is 537. And the actual temperature was 90 degrees Fahrenheit. To convert that to Rankine, we add 460. This gives us 3,188 cubic feet per minute. So let me note that R stands for Rankine, which is the absolute temperature scale in Fahrenheit, and this is 460 is to convert from degrees Fahrenheit to Rankine. We would do the same thing for Q sub B, which started with a flow rate of 2,500 cubic feet per minute. The pressure was 17 psia and the temperature was 110. And we would get a flow rate of 2,724 cubic feet per minute under actual conditions. So now, because these are both in the same temperatures and pressures, all at standard conditions, we can just add them together. QA plus QB, and we get 5,912 cubic feet per minute. And we'll use all of these numbers in the next part of the problem, the flow rates under actual conditions. Now we can use this information to find the total mass flow rate going into the cyclone, because once we know that, 95% of it is discharge, 5% of it gets exhausted into the atmosphere. So we'll find our M total and apply the 95% removal. So our M dot coming from or going into the cyclone is the sum of the M dot going into A, or coming from A, plus the M dot mass flow rate coming from B. This is equal to Q sub C times, Q sub A, the flow rate from bin A, times the concentration in that exhaust, plus Q sub B times C sub B. Let's think about whether we're in standard or actual conditions. The concentrations were given to us in standard conditions, which means that we should use flow rates in standard conditions, which we calculated in step 2. So what we're going to use here is the 3,188 cubic feet per minute. And we'll multiply that by the concentration that we were given in the table, which was 15 grains per cubic feet. And then we'll multiply by the 2,724 cubic feet per minute, which is the standard flow rate from bin B, times the concentration in that exhaust of 10 grains per cubic foot. These have different chemical compositions, but we're just interested in the total mass so we can add them together. And this gives us 75,060 grains per minute. So that's the mass flow rate of stuff that's entering the cyclone. The amount that's discharged as waste out the bottom is equal to 95% times M dot total. So it's 0.95 times the 75,000 grains per minute, which is equal to 71,310 grains per minute. Now in the last part of the problem, we need to figure out the concentration of particulate matter in the exhaust. And so what we can do is to find the mass flow rate of the exhaust and use that combined with the flow rate information to find the concentration in the exhaust. So we know that our m dot total, the amount coming into the cyclone, is equal to the m dot in the discharge plus m dot in the exhaust, right? 95% of it goes to the discharge, the other 5% goes to the exhaust. So that means that our mass flow rate in the exhaust is equal to our total mass flow rate minus that in the discharge. That equals 75,060 minus 71,310, or 3,750 grains per minute. Likewise, I could just take the total mass flow rate and multiply by 5%, and I would get the same thing. Now we know that the mass flow rate in the exhaust has to equal the flow rate of the exhaust, volume flow rate, Q, times the concentration in the exhaust, which means that our concentration in the exhaust, if I just rearrange this, is equal to m dot of the exhaust divided by the flow rate of the exhaust. And so now I can take the 3,750 grains per minute. Remember, we're at standard conditions, and divide by the total flow rate. So the cyclone, the flow all goes through it and comes out as the exhaust. None of it's diverted anywhere. So we take the total flow rate, which was 5,912 cubic feet per minute. So let me make a note that that Q exhaust is the same as our total flow rate. And this equals 0.63 grains per cubic foot. So that is the concentration of solids, of particles, in the exhaust.